Hello class, welcome to Geometry Lesson 9.1, Polygons in the Coordinate Plane. So our central question today is, how are properties of geometric figures represented in the coordinate plane? Our goal is to use the coordinate plane to analyze geometric figures. So this unit is on coordinate geometry, and in order to review coordinate geometry and actually use it, we need to kind of review the distance, midpoint, and slopes that we talked about in the beginning of the year. So you may recall that a distance formula actually comes naturally from the Pythagorean theorem. So if you wanted to find the distance between, say, these 2 points in red, which are connected by a line segment, then that is the same thing as finding the length of the line segment between those 2 points. Now, in order to find the distance between those 2 points, or the length, we need to find the horizontal distance and the vertical distance. So let's go ahead and draw the horizontal distance. Now you may recall that to find the horizontal distance, we subtract the x coordinates. So for instance, that if x1 is, the location of x1 is the number 1 on the number line, and let's say the location of x2 is 5 on the number line, then the distance between 1 and 5 is 4. And you would do that by taking the difference or subtracting the two numbers. And that would give you the distance between those two numbers on the coordinate plane. So x1 and x2 can be any number, any set of two numbers, and you can take the difference to find the distance between them. Similarly for y, you can subtract the two y coordinates, and that'll give you the distance vertically. Now we're going to use the Pythagorean theorem here, so we're going to label the sides A, B, and C. Now that we formed a right triangle, remember that you can use the Pythagorean theorem only for right triangles here, and we do have a right triangle. And remember that C on the right triangle represents the length of the hypotenuse, which is the same as convention that we use here. So we have a squared plus b squared equals c squared. And we're going to replace a with the x2 minus x1 and b with the y2 minus y1. So doing, we have a squared becomes x2 minus x1 squared, b squared becomes y2 minus y1 squared. Now we're going to get rid of the square in front of the c there by taking the square root of both sides. Remember that the square and square root cancels, leaving us with simply c on the left side. And so this is the distance formula. So notice that the distance formula comes from the Pythagorean theorem. So the midpoint formula next helps you find the halfway point. It's literally the middle point between any two set of points. Now in order to find the halfway point between two numbers, like say 1 and 6 or 1 and 5, you had to take the arithmetic average or the arithmetic average of the two numbers. Remember that taking the arithmetic average means adding the two numbers together and dividing them by 2. So if we have these two sets of points and I want to find the halfway point between x1 and x2, I take the arithmetic average between x1 and x2, so I add them up, divide by 2. Similarly, I do the same for y. I take the sum of the y coordinates, divide by 2, and that's the average of the 2 points. And then if I take those 2 points together, the blue and the purple, and I connect them together, they'll meet at the halfway point of the original line segment. And this is the midpoint of the line segment between the 2 red points. So the formula for the midpoint is the average of the x coordinates and the average of the y coordinates. Add them up, divide by 2. The slope recalls the ratio of the vertical change, or the rise, to the horizontal change, or the run, between the 2 points. So if I had the example that I showed earlier, I take the horizontal distance, which remember is x2 minus x1. Then I take the vertical distance, or the rise, y2 minus y1. And so the slope is rise over run, so I labeled my sides here. The slope equals rise over run, which is the same thing as change in y over change in x, the distance in the y and the distance in the x, and I can plug it in. So the rise is y2 minus y1, the run is x2 minus x1, and there's my slope formula. All right, so now that we run over those coordinates, the formulas for, the basic formulas for coordinate geometry, let's go ahead and, given the triangle in the coordinate plane, let's find AB, and then find the point that bisects AB. Finally, we'll show that the angle ABC is equal to 90 degrees using slopes. So first, finding AB, remember that, let's see here. Remember that if I wanted to find the distance from A to B, I need to figure out the vertical distance and the horizontal distance, and then plug it into the distance formula. So the vertical distance here is 6 minus 1, right? In this case, 6 minus 1 is 5, and that's this vertical distance. And then I need to find the horizontal distance right here, and that's simply 1 minus, or 3 minus 1. So that would be 3 minus 1, which is 2. Okay, so we got the horizontal distance and we got this vertical distance of 5. And then we take the square root of the squares of those distances, right? So we have AB is equal to the square root of the x2 minus x1, which is this 3 minus 1, which we got 2. So we got 2 squared plus, and then the y2 minus y1, which is a 6 minus 1, which was 5 squared. And then we go ahead and square them out. We got 2 squared is 4, 5 squared is 25. So we got looks like we have square root of 29. So the distance here from A to B is square root of 29. All right, so now let's find the point that bisects AB. The point that bisects AB, remember, is the halfway point. So we're going to find the halfway point of this part, and then the halfway point of that part. So you just got to take the average of the x-coordinates. So add those x-coordinates together, divide by 2. We'll call that the midpoint M. So we got to add the x-coordinates, so 1 plus 3 divided by 2, then add the y-coordinates, 6 plus 1 divided by 2. We got 4 divided by 2 is 2. Then we got 7 divided by 2, which we can leave as a fraction. And that's our midpoint. Okay, so that's the halfway point between 6 and 1 is 7 over 2, which is 3.5, which is around here. And then the halfway point between 3 and 1 is simply 2, which is this halfway point. And if I put those halfway points together, I get this halfway point right here, which is definitely looks like the halfway point of this line segment AB. All right, now we're going to show that angle ABC is equal to 90 degrees using slopes. So ABC is this angle right here, and we want to show that it's a 90-degree angle, so we want to know what that is. So let's go ahead and prove that that's a 90-degree angle. In order to do that, we need to find the slope. Let me erase all of this first. So we need to find the slope of this and the slope of this. Remember that the slope of two line segments that are perpendicular, the slopes are opposite reciprocals. And that will show that they're perpendicular. All right, so remember, opposite reciprocals means that if you have a slope of 2 over 3, then the other slope is going to flip, called the reciprocal, and it's going to change to the opposite sign. So if this were negative, then this will turn into positive. So the signs are opposite and they're reciprocals, they flip. So that's an example of two things that are that cross at a 90-degree angle are perpendicular. All right, so let's go ahead and find the slope of this. Well, we know that the rise is 6 minus 1, which is 5. And it's actually going down 5, right? It's going down from left to right, and then it's going to the right. So it's negative 5. It's going down 5. Remember, you read it like you're reading a book from left to right. And then from left to right, we're going at a distance of, we did that earlier, that's 3 minus 1, which is 2. Okay, so the slope for this AB part, and we'll write it down here, the slope of the AB part is rise over run. That's our slope so far. Now let's use a different color, and instead we'll do this slope. So we're going to do the rise from left to right, or let's do from left to right. Let's do the run first. Let's do the run. The run is from 3 to 8. So we got to do 8 minus 3. Well, 8 minus 3 is 5. And then we got to do the rise. It's going up, and up means positive. So we're going to do 3, this coordinate of 3, minus this coordinate right here, which is a coordinate of 1. So this is 3, this is 1, which means that's the distance of 3 minus 1, which is 2. So this has to be 2 here. So the rise is 2, the run is 5. So we got the slope of BC is equal to rise over run, 2 over 5. And notice that these are opposite reciprocals. These signs change, right? This is an invisible positive, that's a negative, and they flip. And so if they flip, then that means they're also reciprocals. So that means that's a good thing. That means that they cross at a 90-degree angle, and that means that that right there is a 90-degree angle. So therefore, the measure of angle ABC equals 90 degrees, and that's good. So what we would say is that these are perpendicular. So these two slopes are perpendicular. All right. Looking at the next one, this time we're going to classify the triangle using coordinate geometry, using the formulas. So when you look at a triangle and you want to classify it, you need to use the distance formula. So you're going to find the distance of all 3 sides. Okay, so let's go ahead and get started. Let's go ahead and find the distance for x, y. So this right here. So we need to find the rise part, like the vertical distance. Now the vertical distance, and in this case, we don't care about whether it's positive or negative, because we're going to do the distance formula. And the distance formula has a square. So we're not going to be concerned with it, although I will put the negative sign and a positive sign just in case you want to know if it's positive or negative. So from x to y, it's going to be going up, so that's positive. And the distance is 1, 2, you can count the spaces, 1, 2, 3, 4, 5, 6, which is the same thing as doing 8 minus 2, which is 6. So this is 6. And then we're going to go in the horizontal, 1, 2, 3, 4 spaces. All right. And then to do the distance formula, I take the square root of this squared and this squared. And that'll give me xy. So xy, the distance from x to y, is a square root of the vertical change squared and the horizontal change squared. And then we got 36 plus 16. 4 times 4 is 16. 6 times 6 is 36. And then I add them together, leaving me with the square root of 52. All right, now you can technically break up 52. So let's break up 52 into 4 times 13. And remember, 4 is a perfect square, so you can take the square root of 4. The square root of 4 is 2. So this becomes 2 times the square root of 13. And that just makes it look nicer, getting that radicand as small as possible from 52 to 13. Now let's do the distance from y to z. So we need to do the horizontal, which is count it 1, 2, 3 spaces to the right. And then this is going 2 spaces down. So it's -2. Again, it doesn't matter if you put negative or positive for the distance formula because it's being squared anyways. And a negative number squared is always going to be positive. But I will put it there just to be technically correct. So then from y, the distance from y to z is equal to the square root. We have our run squared plus our rise squared, which is negative. But I told you it doesn't do anything. 3 squared is 9, 3 times 3. Now -2 times -2 is +4. Just as if it were +2 times +2 would be 4 as well. We get the square root of 13. All right, that gives us xy. Now finally we'll do yz, or xz. So let's do the run. Count the spaces, 1, 2, 3, 4, 5, 6, 7 spaces to the right. Then do the vertical, 1, 2, 3, 4 spaces up. So it's going to be xz equals the square root of the run squared plus the rise squared. We got the square root of 49. 7 times 7 is 49. 4 times 4 is 16. We got square root of 49 plus 16. 49 plus 16 is 65. And we can go ahead, we should be able to leave it like that. Let's see here, because it would be 5 times 13. And we know that 5 is in a perfect square like 4 is. So we can leave it like that. And we can see that all these numbers are different, right? This is 2 square root of 13. This is square root of 13. And this is square root of 65. So all the numbers are different lengths, or they're different distances. And because they're different distances, we call that scaling. All right, remember, if 2 of the distances were the same, it would be isosceles. If they were all the same, it would be equilateral. So this is a scaling triangle since xy does not equal to yz, which does not equal to xz. So we got ourselves a scaling triangle. All right, so determine whether triangle xyz is a right triangle. Now, we showed you how to do this by using slopes. But this time, I'm going to show you how to do this using the Pythagorean theorem, the converse of the Pythagorean theorem. So we are going to use the converse of the Pythagorean theorem. Now, the converse of the Pythagorean states that if a squared plus b squared equals c squared for the sides of a triangle, then that means that the triangle is a right triangle. The regular Pythagorean theorem stated that if you started with a right triangle, if you knew that it was a right triangle, then these a squared plus b squared is c squared. So this is the reverse of the regular Pythagorean theorem. So we're using the converse. This is going to help us to prove that this is a right angle here. All right, so let's go ahead and do it. So c is always the longest side. So this is going to be c. This is A and this is B. Doesn't matter which one's A and which one's B. It only matters what C is, which is the longest. So let's go ahead and plug into the Pythagorean theorem. A squared plus B squared equals C squared. So we got A is the square root of 13. Right there. And B is 2 square root of 13 squared equals C, which is square root of 65 squared. All right, now remember that the square roots cancel, so this cancels right here. So you got 13, and then you got 2 squared. Well, 2 squared is 2 times 2, which is 4. And remember that the square root and the square root cancels here, leaving you with 13. You got to distribute the 2 to both of them. And then the square root and square cancel here, leaving you with 65. So let's see if this is true. 13 plus 4 times 13 is 52. And is that equal to 65? And the answer is yes. 13 plus 52 is equal to 65, which means we have ourselves a right triangle. And that is true. That means this is my right angle. How do I know that's my right angle? Well, because the right angle is always going to be opposite of the longest side in the triangle. And the longest side is square root of 65. All right, let's look at ourselves on another example. This time we're going to focus on classifying quadrilaterals. In fact, that is the main part of the lesson, is actually looking at a bunch of quadrilaterals. This is a review of chapter 6, so we got to classify whether this is a parallelogram or not. Remember that a parallelogram has 2 opposite sides, 2 pairs of parallel sides, right? So those have to be parallel and these have to be parallel. In order to do that, we need to prove that the sides are parallel by finding that the slopes are equal. So if I calculate the slope of this and then the slope of this, they should have the same exact slope, same rise over run. Same thing for the double arrows. They should have the same rise over run. Okay, so let's go ahead and prove that. We don't know that yet until we prove it. So let's go. We're going to do the rise over run for this. This is going to be the distance from 5 to 8. That's 3 jumps. 1, 2, 3. So the rise is 3, the run is 1. So let's calculate the slope of RS, which is rise over run. 3 divided by 1 is 3. So we got that slope. Now let's do this slope. We're going to go to the right 1, and we're going to go up 3 spaces, which means it's the same exact slope. So the slope of UT is rise over run, which is 3. This means that those are parallel. Remember that symbol? The symbol with the 2 vertical bars means parallel. So these are parallel. We have proved that. Next, let's look at the slope for ST. So it's going to go to the right. 1, 2, 3, 4, 5, 6 spaces to the right. This is going down 1, 2, 3, 4 spaces, which is down is negative. So it's going to be negative 4. So the slope of ST is rise, which is negative 4, over run, which is 6. We can reduce this by dividing by 2, leaving us with negative 2 over 3. And remember, we like to simplify the fraction as much as possible. Now, let's do the same thing for RU. It's going to go down 4, and looks to be over 1, 2, 3, 4, 5, 6. So that means looks like we have the same slope. RU is rise over run, which if we reduce it, leaves us with negative 2/3. So these are parallel as well. So these are parallel, and the other two are parallel, which makes this a parallelogram. All right, let's look at another quadrilateral. Determine whether the given figure is a trapezoid. Remember, what makes a trapezoid and not, for instance, a parallelogram is that a parallelogram has 2 pairs of parallel sides. A trapezoid has only 1 pair, namely that pair. So we still got to calculate all the slopes for the trapezoid and determine that only 2 of them, the opposite ones, are parallel. And then the other 2, the legs, which we call them, are not parallel. So we got to show that the legs are not parallel, but the bases are parallel. All right, so in order to prove this, we're going to do the slope, which is rise over run. So let's go ahead and do the rise here. So it's going up 1, 2, 3. The run is 1, 2, 3, 4, 5, 6. So it's running 6. Let's do this bottom base while we're at it. It's going to go up 1, and then this one's going to go over 1, 2. So let's go ahead and calculate the slopes. Let's do BC. The slope of BC equals rise over run. Remember to reduce this by dividing by 3. You want to divide by the greatest common factor of both the numerator and denominator. So 3 divided by 3 is 1. 6 divided by 3 is 2. Let's do the slope of AD, which is rise over run. So these match up, which means that they're parallel. So that's a good thing. Let's do the last pair. So let's do it's going to go down 1, 2. This one's going to go over 1, 2, 3. So the slope of BA is negative 2 over 3, which is not the same as 1 over 2, which is good so far. Now we're gonna go run 1 and rise 1, 2, 3, 4. So the rise of 4 over 1. So we got the slope of DC is rise over run. And notice that these are not equal to each other, so they're not parallel, right? So therefore the 2 legs are not parallel, but the 2 bases are parallel, which makes this a trapezoid. All right, so let's go ahead and classify a kite. What makes a kite a kite? Well, the thing that makes a quadrilateral a kite here is you have 2 consecutive sides. Consecutive means, they're next to each other, they're adjacent, and these 2 adjacent sides are congruent. So you have 2 pairs of this. So you have these 2 adjacent sides are congruent, and then these 2 adjacent sides are congruent. That's what makes it a kite. The opposite sides are generally not congruent. Only the adjacent sides. So we have to show that this is congruent to that and this is congruent to that. So let's go ahead and show that. In order to do it, we need to calculate the distance. So let's do the rise and the run, but this time not calculate the slope, but the distance. So the rise, or the change in the y, is, let's see here, 1, 2, 3 spaces up, and this one's 1 space to the right. And so if I do the distance formula for that, that's the distance for KL is the square root of the 3 squared plus the 1 squared. And we got 3 squared is 9, 3 times 3 is 9, 1 times 1 is 1, 9 plus 1 is 10. So I have the distance of square root of 10. Now let's do the distance from L to M. That looks like it's 3 spaces to the right and 1 space down, which is -1. So the distance of LM is the square root of 3 squared plus -1 squared. But remember, -1 squared, it doesn't matter if it's negative, so it's still going to be the square root of 10. So these are congruent. So these are the same length. Now let's do KJ, and let's actually do it in another color. So we're going to go down 1, 2, 3, so down 3 over 1, 2, 3, 4. This one's going, well, this one's pretty easy. This one's only going 1, 2, 3, 4, 5 units up. So the distance of that is 5, and that's it. So the, and oh, I said M for distance. It should just be KL and LM for the distance. I apologize for that. Remember that the little m here stands for slope, and we're not calculating slope, we're calculating distance. All right, so MJ is equal to the square root. Oh, MJ is just 5. We just calculated. MJ is 5. There's no need to do the distance formula for this because it's just 5. It's just 5 units up. It's only useful to use a distance formula if you got something diagonal, right? If it's straight, if it's horizontal or pure vertical, don't worry about it. So we got the distance from K to J is the square root of -3 squared plus 4 squared. Now, remember, -3 squared is 3 times 3, which is 9. And then 4 times 4 is 16. 9 plus 16 is 25. And the square root of 25 is 5. Which means that these are congruent, which is exactly what we set out to prove. Therefore, we do have ourselves a kite. 2 consecutive pairs of congruent sides. So remember, we said that we have 2 congruent pairs of consecutive sides. All right, let's go ahead and summarize what we did in this lesson. Well, and let's summarize quadrilaterals, really. I want to show you, since we didn't go over every single case of proving a quadrilateral, let's go ahead and go over quickly the methods of how you would prove various quadrilaterals. We talked about the parallelogram. We mentioned that one of the methods that we used for the parallelogram was to calculate the slope 4 times, and in order to show that we have 2 opposite sides are parallel, right? So when we had a parallelogram like this, we showed that this was parallel and this was parallel, and we did that using slopes. And that was using method 2. You can also show that as a parallelogram by instead showing that the distance here is the same as the distance there, and the distance here is the same as the distance there. That would be using the distance formula 4 times, right? And that would be method 3. So there are a bunch of ways that you can prove things that are parallelograms, and these are 4 of the methods. I went over 2 of the 4 so far. Now, if you had a rectangle, what makes a rectangle special is that 1, it has 4 right angles, right? And that's what makes it a rectangle, is having the 4 right angles. So you can use the slope formula 4 times to show that the slopes are opposite reciprocals, and therefore they form 90-degree angles. That's method 1. You can also prove that this is a parallelogram by doing this, right? Showing that those are parallel. That's just showing that it's a parallelogram. And then you can use the distance formula to show the diagonals. Okay, so let's talk about that. Remember that in a rectangle, because the angles are 90-degree angles, that means that the diagonals are the same length. So this diagonal, which is AD, is the same thing, is the same diagonal as, well, let's call this AC. It's the same diagonal as BD. Okay, so these are the same length, and that's only true because of the right angles. So if you calculate the distance of the diagonals and show that they're congruent, then it's going to be a rectangle, as long as you showed that these other ones, as long as you showed that it's a parallelogram as well. So prove that it's a parallelogram first, and then use the distance formula for the diagonals to see if they're congruent. Okay, and that's just another example of how to prove the rectangle. For the rhombus, remember the thing that makes a rhombus is that it's a parallelogram with all sides congruent, right? So all the sides are congruent in a rhombus, and the rhombus is a parallelogram. So you can use the distance formula 4 times to show that it's congruent, and that will be pretty straightforward to do on a rhombus. And that would also show that it's a parallelogram because remember the opposite pairs are the same. The two pairs of opposite sides are the same, so automatically a rhombus. You can also prove that it's a parallelogram by doing the parallel stuff, and then use the formula to show that the diagonals are perpendicular. So in a rhombus, the diagonals cross at a 90-degree angle. All right, so you can do that as well. The square, remember the square is a combination of the rhombus with the same sides here and the rectangle with the 90-degree sides. So if you prove that it's a rectangle and then prove that it's a rhombus by doing the sides are the same, then you can prove that it's a square. All right, so that is essentially right here, that's essentially, where is it? Rectangle, proving that it's a rectangle, and then using the distance formula for two consecutive sides to show that they're congruent, make it in a square. So that would be like method 2. All right, so finally we got the kite. For the kite, we did that earlier. If you show that two sets of consecutive sides are congruent, so if you have a kite here, showing that these are congruent and then these are congruent, then you can show that it's a kite. And then finally, we got trapezoid and isosceles trapezoid. We talked about the trapezoid. Use the slope formula to show that only one pair of opposite sides are parallel. But for the isosceles trapezoid, we didn't do an isosceles one. But to prove that it's isosceles, you got to show that these are parallel, but that the legs are congruent. So you got to calculate 4 slopes and then two of these distances to see if they're the same. So use the distance formula twice for the non-parallel sides to show that they are equal, making it isosceles. All right, that's going to do it for the video, guys. I hope you found this useful. I hope you took a few things and learned. And as usual, I'll see you in the next one.